All right, this is our very last lecture for 7.4 and for the school year. So we are looking at the fact that we are looking at conservation of momentum, but we're going to look at another case of conservation of momentum. In the last section, we looked at what if we have two objects that initially at rest that then move apart. We have an initial momentum of 0, and we have to have a final momentum of 0, so those two are equal. What if instead of starting together or moving apart, what if we start apart and smash them together? That's when we get collisions. Right? There are three types of collisions. There's an elastic collision, in which all kinetic energy is conserved, an inelastic collision, or in which some of the kinetic energy changes, and then a completely inelastic collision in which our objects stick together. All right? So those are our three types of collisions that we're going to talk about. I will tell you that elastic collisions are really, really hard to model in the real world. The closest thing that we can get to that is billiard balls or pool. Right? Most cases are inelastic or completely inelastic. Right. So we've already looked at the fact that we are having some changes in energy. In an elastic collision, we have no loss of energy to heat or deformation. Our object may temporarily change shape, but overall its shape remains constant. If you've ever seen a slow motion video of a golf ball being hit, that golf ball is actually going to flatten on one side as a part of that collision, and then it's going to return to its normal shape. All right, so that's essentially an elastic collision. In an inelastic collision, some of our energy is converted to sound or heat, or actually changing the shape of the object. In a completely inelastic collision, we're all going to see that kinetic energy being converted to sound, heat, or changing the shape of the object, specifically the fact that our objects are sticking together. Okay. Just like we looked at before, we are looking at momentum conservation. The total momentum is the momentum of each individual piece inside of our system. So we have two objects here, and the total momentum is the momentum of each object. Right? So we're going to use that idea to do an example problem. Right? Just to talk about the fact that this is a collision, so we are going to start with the premise that PI is equal to PF. Our initial total momentum is equal to our final total momentum. So, on a touchdown attempt, a 95-kilogram running back run towards the end zone at 3.75 meters per second. A 111-kilogram linebacker moving at 4.10 meters per second meets the runner in a head-on collision. If the two players stick together, what is their velocity immediately after the collision? So let's go ahead and take a look at what that looks like. So I have my running back here. He's got our football. And I'm going to call him object 1. He's moving this way towards the end zone. And then my linebacker is like, nope, not going to happen. He comes in, and he's running this way. I'm going to call him object 2. Once they collide, a big, nice crash, they're now going to be stuck together. And they're going to move together in one direction or the other. We don't know which. Right? So let's go ahead and build this. Initially, they are individual objects. It's that M1V1 plus M2V2. After the collision, they're now a combined object because they're going to move together with the same speed. All right, so that's sort of what we're looking at here. I identified equations, and I did a couple things out of order. So let's go ahead and backtrack to make sure we're getting all the pieces we need. So we have our M1 is equal to 95 kilograms. And our V1 is equal to 3.75 meters per second, and we have established the fact that that's going to be in the positive direction, so we're going to make this positive. M2 was 111 kilograms, And V2 in a head-on collision is going to be moving in that negative direction. So that velocity is going to be negative. All right, so we've identified that. And we want VF. So now we're going to go ahead and set these two equations equal to each other. We have M1V1 plus M2V2 is equal to M1 plus M2VF. All right, we're solving for VF, so we're going to divide both sides by that sum of masses here. And when we do that, I get VF is equal to M1V1 plus M2V2 divided by M1 plus M2. Right. So now we can go ahead and plug and chug the information that I've gone ahead and set out over here. It is important to make sure that you are keeping track of your positives and negatives, because that will affect what direction this velocity is as a result of our math here. All right, so I have 95 times 3.75 plus 111 times negative 4.10, and all of that is divided by 95 plus 111. And we do get a negative answer here because this linebacker did have a larger momentum. So our final velocity is negative 0.4798543689 meters per second. Obviously, that's not to the correct number of sig figs. We do get 3 sig figs in our math, right? So we get this one, and this one. So that goes ahead and rounds this to our final velocity of negative 0.480 meters per second. All right. So that was a general idea of looking at the conservation of momentum in terms of collisions. Now, because they stuck together, that was a very specific type of collision. That was a completely inelastic collision. Now we're going to look at elastic collisions. Not only do we conserve momentum, but we also conserve energy. All right, so our final kinetic energy is equal to our initial kinetic energy. All right. This is the equations that we are going to use for the case of perfectly elastic collisions. This only works if your second object is initially stationary and the initial velocity of your first object has a speed v. These come from a very specific place. All right, if I back up just a minute, we're looking at this idea. So if I were to expand these out for two objects, my initial momentum is m1v1I plus m2v2I is equal to m1v1f plus m2v2f. The only thing we know in the equations we're looking at on the next slide is the fact that v1I is equal to v and v2I is equal to 0. And technically we know some masses. So that goes ahead and simplifies this equation. Right? That leaves us with too many unknown variables. Because generally speaking, you'll know your initial velocity and you know your momentums, but you may not know both final velocities. So that leaves us with too many unknown variables in one equation. So that's where the kinetic energy actually comes in. We're building the same idea, but we're using the kinetic energy equation. So your initial kinetic energy is 1/2 m1 v1 I squared plus 1/2 m2 v2I squared equals 1/2 m1 v1f squared plus 1/2 m2 v2f squared. We're still going to use the same premise of the fact that v1I is v and v2I is 0, so this term goes away. All right, and this term turns into a v. So I have the 1/2 m1 v squared is equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared. I'm not going to go through the rest of the derivation. All right, so that's crooked. I'm not going to go through the rest of the derivation, but these two equations, built from the conservation of momentum and the conservation of kinetic energy, are where these two equations come from. All right, so make sure that you get these in your notes. If you are looking at a problem where your second object is initially stationary and your first object has an initial velocity and it is a perfectly elastic collision, these are the two you go to. It does have to say that it is an elastic collision, not an inelastic collision. All right, so let's go ahead and do an example problem here with an elastic collision. We have an amusement park with a 96-kilogram bumper car moving with an initial speed. This goes ahead and tells us this is already our first object. So this is m1 is equal to 96 kilograms. v1I is equal to 1.24 meters per second. And it bounces elastically off a 135-kilogram cart that is initially at rest. Right? We want to know the final velocities of the two cars. So we're using, like I said before, these two equations. So v1f is the difference between the masses divided by the sum over that velocity. So v1f is equal to m1 minus m2 over m1 plus m2, and that's times rv. And then it's 2m1 divided by that sum. All right, so we have all this information. We have our mass, we have our velocity. We can go ahead and plug and chug. So for v1f, we are looking at 96 kilograms minus 135 kilograms divided by 96 kilograms plus 135 kilograms, and this whole term is multiplied by the 1.24 meters per second. Notice that that top is going to give us a negative number. Right? So this should help sort of solidify the fact that it bounces off elastically. So the car, so we had m2 was here, m1 was here. It came in and it bounced back elastically. Right? So it's moving in the opposite direction it was before. So this is negative 0.209 meters per second. All right, we're going to do the same process for V2F. So V2F is 2 times the 135 divided by 96 kilograms plus 135 kilograms, and this is times the 1.24 meters per second. And we do get a final velocity of 1.45 meters per second. All right, so that's what we have going on here for that conservation momentum in an elastic collision. So you do have homework of the 7.4 lesson check. Please make sure that you do that. It is a modified lesson check, so please make sure that you look at what those numbers are in the agenda. Have a wonderful day.